Okay, so I think we'll go ahead and get started. Hello, my name is Bradley. So I'm on the Parachains core team with Parity, along with Mache, and I've done some work on things like execution cores and asynchronous backing. Today I'm going to be talking to you about data availability and sharding, as well as Cumulus, which is sort of the parachain side of the Polkadot protocol. Fun fact, I was a student at the first Polkadot Blockchain Academy, so it's nice to be back and go from student to teacher. Let's jump into it. At least if my clicker works. There we are. All right, so for a quick outline, we're going to cover the data availability problem that Polkadot has, what solution we have made, how erasure coding is involved in that and what erasure coding is, and then some ongoing work we're still doing to improve this part of our system. Clicker is not always working. It is on. Okay. All right, so what data needs availability in Polkadot? So we have this sharded permanent record that goes on parachains. Then we have this condensed permanent record that goes on the relay chain, which I forgot to kick on my speaker notes for you guys. Let me go ahead and split off this screen onto a separate screen so I can have my speaker notes going. May need a tiny bit of help with that. No? Let's see. Now I know it's yeah, it's like a system settings, display. Use add. Nice.
And then whatever you want to show them, you drag on your screen.
Yeah. All right. There we are. All right. Technical difficulties overcome. All right. So again, we have this, most of the data that we're dealing with, we want to take advantage of sharding, right? So that's going to live on parachains. But then we have this condensed data, hashes and commitments and whatnot, that's going to live on the relay chain in a permanent record. But we have this third kind of data, which is this comprehensive 24-hour record, and we need that information. It's critical to secure the progression of parachains. And then we drop it later from validators when it gets old, we no longer need it. And the reason why we can't put this data on any chain is because it's very heavy. It's measured in megabytes. So let's state our data availability problem. So how do we ensure that a piece of data is retrievable without storing it on every single node forever on chain? And incorrectness can't be can be proven, but unavailability can't. So you can't just hold a small number of nodes accountable for making some data available. You have to actually find some broader solution. And that solution does very much need to be off-chain. For context, all the data that ends up on the relay chain in a day is about 555 megabytes. If we were to put say for 40 parachains, all of their proofs of validity for every block on a chain for a day, that would be about 72 gigabytes. And that is data that we are keeping forever. And that nodes are going to have to replicate forever. So it's really not an option to be storing that much on chain. All right, so let's take a look at the data availability problem and why these proofs of validity that I've been mentioning. Again, to repeat some of what Maciej said, these are a bundle of data that's necessary to verify that a particular parachain block sort of obeyed that parachain's own rules. And we need that as validators in order to secure the parachain, in order to run that parachain state transition function. Now we need that data, we need it to be made available, and here on the parachain side, we're looking at one way that the passing of that data can break down if there are malicious actors. So we have on the bottom right here a withholding block author. So they are authoring a parachain block, they are passing a proof of validity up to the Polkadot validator set. Maybe it's a valid proof of validity, so it goes through the Polkadot parachain's process by which that block becomes included in a relay chain block and eventually finalized. All of this can happen without that block author telling any other parachain nodes about the block they just made. So a block can become finalized, a parachain block can become finalized without its author telling any other parachain node about it. This is kind of a unique problem to Polkadot, and so we had to make kind of a unique data availability solution. Now, a couple of the things, I'll go back. A couple of the things that happen when other parachain nodes are unaware of the latest block, it can prevent users from learning about parachain state, and it can prevent other collators from being able to create blocks. Because if the best block on a parachain, the newest block, is only known to one collator, the other collators can't build on top of that. They have not executed the transactions within that block, they haven't updated their state, and so they can't build any further blocks until they catch up. And that's where, if my clicker works, there we are. That's where Polkadot data availability comes in. The Polkadot validator set keeps enough info for collators to reconstruct recent parachain blocks. And that information will be made available to parachain nodes when they request it. They'll essentially say, oh, I've seen this candidate receipt on chain for a block for my parachain, but I haven't seen that block. And it's been a little while now. I should have seen it by now. I'm going to go and request it from the Polkadot validator set. We still do keep just normal gossip between parachain nodes as the primary way of passing around parachain blocks, rather than relying on data availability for all of that, because let's just say it's processing and network bandwidth intensive for the Polkadot validators to provide these blocks back to parachain nodes, but it's important that we still have that process available. All right, so I described a problem that happens that data availability can solve on the parachain side, but there is also a problem that data availability can solve on the relay chain side. So in this case, instead of a collator withholding its blocks from other parachain nodes, instead we're going to have a malicious backing group. This group has already backed a block that had an invalid proof of validity, and now they're, well, let's consider first the situation where Polkadot has no data availability layer. We know that the backers have the proof of validity because they just executed the block in order to back it. If we were to trust the backers to simply distribute that proof of validity to approval checkers later on, then the backers could kind of pick which approval checkers actually get that important information. Now, Mache went over, the odds of, say, 30 out of 30 approval checkers being malicious from a small set when you're picking them randomly is very, very small. And we only normally need one honest approval checker in order to trigger a dispute and then cause this escalation. That's how the security model of approvals works. But if you have a malicious set of backers that are not willing to distribute the proof of validity to honest approval checkers, suddenly that all breaks down. You don't even have one honest approver who can check a block in order to dispute it. And because of that, this is really, really bad. This is where a small cohort of malicious backers and malicious approval checkers could just submit parachain blocks to the relay chain, have them approved and finalized that, say, loot accounts on a particular parachain, or pick your poison of all the wrong things that could happen. So we introduce a data availability layer. Suddenly our malicious backers, they have to submit this proof of validity to the data availability layer of Polkadot, and the data availability layer has some stronger guarantees on its integrity. Essentially, we restore that 1/3, less than 1/3 dishonest, failure condition. Or no, it would be more than 1/3 dishonest failure condition that we restore. And so our data availability layer is very likely to be honest. Once our backers have passed the proof of validity to the data availability layer, then it's the responsibility of that data availability layer to pass it on. So approval checkers, both honest and malicious, will get the correct proof of validity. And so if malicious approval checkers were to try to, approve an invalid proof of validity, we would appropriately get our honest approval checkers calling that out and triggering a dispute. All right, next we're going to talk about how Polkadot's data availability solution is composed. So we've discussed kind of the problems that having a good data availability layer can solve, but how are we building this thing? How are we making it efficient? So let's start with some design considerations. So we want to avoid storing the full proof of validity in each validator, even off-chain. It's particularly bad if we store it on-chain, because then it's there permanently and needs to be kept as a part of a record forever. That's really bad. But even if we're storing it off-chain, that's still a lot of data. So yeah, passing full proof of validity copies to a large fraction of validators would work, but we can do much better. Misbehavior up to 1/3 should be accommodated to match our threat model as well. Let's see. We want to avoid fragility, where misbehavior can compromise proof of validity retrieval. And we need some cryptographic scheme to prove availability before approvals start. Because if anyone can lie and say that something's available when it's really not, suddenly our, say, finalizing an invalid block problem comes back on the scene. And finally, we need a way to verify that the retrieved proof of validity is actually the same proof of validity that backers initially distributed to the data availability layer. All right, so in order to lay the foundation for us to understand some of what I'm going to be talking about moving forward, we need to talk about execution cores a little bit. So Mache mentioned them briefly earlier. They are the minimal unit of Polkadot execution scheduling. In our current paradigm of parachains, you would typically have one parachain paired up with a single execution core. And the assignment of those parachains to execution cores rotates. That's kind of how backing groups rotate between parachains over the course of a session. And at most, one candidate can be pending availability per relay block per core. So this is kind of the fundamental way that execution cores gate all of the processing that goes on within Polkadot. For instance, even say the collators, as they're producing candidates, collators actually choose not to produce candidates until the candidate from their parachain that's currently occupying an availability core is fully made available. So like even from the very start where collators are building blocks, this is all being mediated by this notion of an execution core. As I hinted at there, the core is considered occupied while there is a candidate paired with it that is pending availability. Oh, a candidate? So a candidate is a parachain block candidate. So this is a block that was produced by a collator and then passed up to the Polkadot validator set and is going through the parachain block validation process. Now, a note with execution cores with regards to data availability is it saves resources to bundle signals about availability for all the different cores together. So we're going to see that a bit later. All right, so laying a little more foundation. Maciej talked briefly about, Sure, I'll take that question.
For the cores, do we map them to like real cores of different machines? So like if a machine has 4 cores, we have 4 cores or how?
So the notion of cores, it's more of an intuitive unit than it is actually mapped to any kind of hardware. So a core, well, you could say that in a way it maps to validator, say, storage and execution. So there are all these different things that are gated by an execution core. It would be, say, are validators willing to check a parachain block in the form of approvals? Are backers willing to check this parachain block to decide whether they want to, say, sponsor it and be on the hook for it? Are data availability participants, so the validator set, are they willing to receive chunks of the proof of validity for that particular candidate? Are collators willing to produce a new candidate in the first place? All of this logic, like all of these gates where either a network participant chooses to do something or doesn't, those are all gated by this idea of an execution core. Like, do we have an execution core assigned to our parachain? Is that execution core already filled with a block from our parachain? Is it currently vacant?
Is this unit the same? So we say that we benchmark on something, and then we say that for a core unit we need this much, and then virtualize on top of cores, or how?
I suppose so. There is reference hardware for the Polkadot validator set, and in a sense, execution cores divide up the efforts of that validator set into equal chunks. So the efforts of the validator set should be equally divided, and in that way, the processing power and storage per execution core is standardized.
Just to interject for a second, there is no direct one-to-one mapping from the Polkadot core to the processor CPU core in your hardware. Think of it as like a VM. Polkadot is a VM running on the hardware, but there is no one-to-one correlation between the hardware core and the Polkadot core. They serve on an abstract level a similar responsibility. That's why we name them as cores, but it's not core because they use the hardware core.
Yeah, and I would add to that in the sense that we could describe Polkadot or the Polkadot parachain system as like one giant meta computer. Like a core is one unit, or like one unit of computation
And
that
this
is
unit-
available on that sort of meta computer, but it doesn't map to, say, a CPU core on any particular machine.
Understood. But this unit is the same. So like they are all the
Yes.
same power, right?
Yes.
Homogeneous, not.
Yes, and then the idea would be, say, if you had a parachain that needed more throughput, then you would assign multiple cores to it. And moving forward, we may also be able to support the idea of assigning, say, less than a core worth of execution to a particular task, be it a parachain or some fancy like core jam idea down the road.
So one more question. You mentioned you can give a parachain multiple cores, and previously it was mentioned that it will always be one core per block per
Yeah, that is
parachain.
currently accurate, but in the future will not be accurate. It's like parachains, by default right now, they are paired with a single core at a time, and then which core is paired with them swaps out. But in the future, it may be that, we guarantee that a parachain has 2 cores at any given moment, but which 2 cores those are swap out. So this is kind of an evolving model as the needs of Polkadot's clients evolve. As they need more execution power, we can assign them more cores, or at least we're working on it.
Cool, thanks. I mean, I have more questions about this, but I will take it offline, like especially the multiple cores one.
Yeah.
Thank you.
All right, we have another question in the back.
Hi, it's really just to get a bit more clarification on the core aspect. I think you mentioned essentially it's like an abstraction on everything that is happening at a particular point in time between the validators, the correlators, and
yeah.
recording, right?
Yeah.
Okay. And so then is this entire thing of a core constrained to a notion in time? Like, for example, when the validators are receiving a particular block and put in a relay chain, or can you elaborate a bit more on that?
So there's this notion of, well, really the way we coordinate around cores has to do with the data availability layer. That's why I went to kind of describe cores in this lecture. A core is considered occupied when a candidate from a particular parachain is sort of pending availability for that core, and that's how we essentially fill a core and then coordinate all of the decisions that are being made around cores. Like I described, those sort of several layers at which decisions are being made. It's, will the backers decide to back candidates for a particular parachain? Oh, do they have a core assigned? And if there's a core assigned, then is it already filled with a candidate? These are the kinds of considerations that we're kind of gating. We gate execution at various points based on the core, but then the core itself doesn't have any execution assigned to it.
Got it. I'm starting to kind of understand. Thank you.
And generally, each core will produce one block every 6 seconds. So the timing question.
Mm-hmm. All right. So I see no more questions. Oh, there's a question.
Is it same like calculating the, like we saw in the substrate, the calculating the weight, and depending upon the weight, we include the number of transactions and exclude, leave others, which cannot be included in the current block. The same in core time also, like they evaluate the weight and they take the transactions from multiple candidates, or is it still dedicated for one, even when they don't have much transaction?
So for now, it is like one parachain block, one candidate per core, per relay chain block, and that's just kind of a nice constraint to make things work for the time being. But like you were saying, there's room for metering, there's room to pack more work onto the same core. If it has a certain capacity, why don't we use that whole capacity? And that is something that has been discussed and is planned. Of course, plans are all up in the air with Polkadot 2.0 and whatnot, but yeah, that definitely is being discussed, and we see a path forward for making that happen based on benchmarking and whatnot.
Got it. Thank you.
Welcome. All right. So with this erasure coding, we have a goal. We want to avoid storing the full proof of validity on each validator. And we have these information chunks that make up that proof of validity. Say, look at our section 1 here on the far left. We have K chunks of information. What we do is we code those chunks into a larger structure that has in chunks. And what we get out of that is that any K subset of in chunks can be used to recover the entirety of the original data. So in this case, we start with 2 chunks of data that make up, say, a proof of validity is how Polkadot uses this. What we would do is we would encode these 3 additional chunks. These chunks are derived data based on the data that's actually in those initial K chunks. And any K out of those in chunks can then be used to recover the entirety of the original information. And we'll get into how that works in a bit. Maciej covered it at a cursory level in his prior presentation. But for now, we can let that be a little bit of magic that is very helpful to us. So in code, what that would look like is you have this data. We can treat it, for the purposes of erasure coding, we don't have to know that that data is a proof of validity, that it contains, a sparse state tree and a bunch of transactions. We don't need to know that. All we need to know is that it's a vector of bytes, and then we want to turn that data into a bunch of chunks. And those chunks are also vectors of bytes, and they need an index assigned to them. So we have an encode process that takes in our data and outputs some chunks. Then we have a reconstruct process that takes in chunks and spits out our original data. So in a black box that way, that's what's going on here. So each proof of validity is divided into a number of chunks equal to the number of validators in the validator set. And the validator with index I gets a chunk with the same index from each proof of validity. Then validators sign statements when they receive their chunk. And once we have 2/3 plus 1 of signed statements, that proof of validity is considered available. Finally, any subset of 1/3 plus 1 chunks can recover the original data. So the proof of validity in this case would be K chunks from the erasure coding slide. And what we're doing here is we store 3K worth of chunks, essentially 3 times the proof of validity size. We store that among our validator set, and that's what gives us our 1/3 plus 1 number here that you see on our final bullet point. Is we only need 1/3 of the original data to have K chunks worth of the original data, and with our erasure coding, that's all the chunks we need, and then we can reassemble the original data with that 1/3. So how do we get our 2/3 plus 1 from the second to last bullet point? That is, we are accounting for a potential up to 1/3 of validators who are behaving maliciously. So if we have 1/3 that are lying about having their chunks and another third that actually do have their chunks and are willing to pass them on to approvers, then we are still good. We have our 1/3 that we need for erasure coding to reconstruct. Oh, and when the POV is later retrieved by approvers, chunk validity is verified using a Merkle proof, and we'll get into the details of that in a bit. We have a question.
When you say validator with the index I gets a chunk with the same index, from who does it get? Does it also know the entire POV, or how does it know that it actually got a chunk of index I?
Yeah, so basically what happens here, and I'll actually move to the next slide for this one because it's partially covered by the diagram there. I might just have to stop using this clicker. It's really not doing it for me. All right, so the distribution of chunks works in this way. So the backing group for a particular candidate, we know they have their chunks because they have already backed the candidate. They have run the parachain validation function on this proof of validity. They have the proof of validity. So what happens for the data availability distribution is validator I sees backing statements on chain. So they see that these backers have placed statements on chain. Those blocks have been gossiped. They see those statements. And then they request chunk I from any of the backers in the backing group. Now, backers either respond with chunks or eventually availability would time out, but that's a different discussion. Now, how do we verify that the chunks that the backers spread around are actually the right chunks? The answer here is in the candidate receipt, which the backers placed on chain with their backing statement. The candidate receipt has something called an erasure root, and we check those chunks against the erasure root when we actually don't check them at this phase. We, for the time being, guess that the backers have distributed data faithfully, but when the chunks are actually retrieved by approvers later, they check the validity of each chunk, or the integrity of each chunk rather, against that erasure root using Merkle proofs. So the chunks themselves have been placed into a Merkle tree structure, and from that we are able to check them.
So does this happen also with the backers? Because I was understanding that this is happening with like the approval part, right? After the back, does the backers have all the proof or not?
Yeah, so the backing group does have the entire proof of validity, but what we can't do is we can't trust them to actually make that available to others later. So what we have to do is we have to kind of pull it out of them, say, hey, backers, give us our chunks for this proof of validity, and once the backers have faithfully distributed all those chunks, then we can move on to the approvals phase.
So the backers themselves, so the module that does this availability and the chunks lives on the backers, they run it and send the chunks to the other validators.
Yes.
How is there a way to, I mean, the validator set changes, right? And like maybe a new validator comes, maybe a validator gets out, or is there like some kind of ordering to know which I is going to a specific validator from all the backers, or doesn't matter? You get what I mean?
I'm not actually sure like which of, say a quorum of 3 backers went and backed a particular candidate. I'm not sure whether any of those backers individually are assigned, say, particular validators to send chunks to. It is those validators, say validator I, will request their chunk, and then a backer will respond with that chunk is how it's done. And then when the validator set changes, then, we get a lot of changes. Like the backing groups are split up, and the actual validator set might change, so some of the people involved in availability might not be around anymore. So there are a lot of complications around those session boundaries, but those last for only about a block, and then things get back to normal. Typically, I mean, the way you might see this impact the chain would be that there's like a temporary slowdown where blocks are not being included or not being finalized very quickly right around the session boundary, but it's such a small period of time that it's not a big deal to take that performance hit.
Thank you.
All right, so we covered how these chunks are distributed, but we need to cover the format in which these, I guess, these chunks are, or statements about these chunks are actually given back and reported. And we want to sign these statements about which chunks we have as a validator, but signing is a little bit expensive, especially if you're going to do it over and over for, say, 100 different execution cores. That's more signatures than we need. So what we use is a structure called a bit field. Each bit represents a single availability core, and if the bit is a 1, then from the perspective of a single validator, it says, I have my chunk for availability from this particular core. So if there's a proof of validity, a parachain block candidate associated with that core at this moment, and if I have a 1 in my bit field for that core, that means I have my chunk for that proof of validity. And so each validator will have a bit field. If we have 100 cores, that's 100 bits, and it's a bunch of zeros and ones, and it just says, from my perspective as a single validator, I have, 40 chunks that are for, 40 different cores within the set of 100, and here are the other ones that I don't have. And it's important that the validator signs this, because that's proof that this is from the perspective of this particular validator, and not just made up information by someone malicious along the way. So these bit fields, they're very convenient because they're a minimal structure to be signed and gossiped around. They're very lightweight, and eventually, the real reason why they need to be very lightweight is that they are submitted on-chain by block producers, and we'll get to why that is. So with availability on-chain, here's a little pairs inherent as pulled up on Polkadot.js. So you can see a couple layers down that we have this object called bit fields, and it's a vector that has a bunch of different bit fields. You have a bit field associated with validator index 0, and it has this vector of bits within it. And those zeros and ones in that bit vec, those represent, I have this chunk, I don't have that chunk, I have this chunk. Like this validator is stating exactly which proofs of validity they have their chunk for. We collect a bunch of different bit fields, and then we calculate from those, from the statements of all of these different validators, okay, which of these proofs of validity do we actually have our 2/3 plus 1 of stated, I guess, stated chunks for. So to visualize this, we have a nice little visual here. Validator Y, in this case, or VY, is producing a block. We have statements from validators A, F, G, and B that determine availability for blocks occupying 5 cores. So each row is the statement from a particular validator, and each column is I guess, all of the statements about a particular candidate. So if we're looking at our columns here, we have candidates 0, 3, and 4 that are marked as included. We have over our 2/3 plus 1 threshold covered for those candidates, and you can see that that's either 4 ones, so either 4 yeses, or 3, because 3/4 is still above our 2F plus 1, and 100% is also above our 2F plus 1. But for those which only had 2 bits that said yes, we only have 2 chunks, and we need at least 3. So these are not marked as included during this relay chain block. They would have to wait until more bit vecs come in that maybe update our information. Maybe validator F suddenly next relay block delivers a bit field that says they have all of their chunks, and then we're off to the races on all of these candidates. Now, when a candidate is marked as included, approvals start for that candidate, and cores are freed up to repeat the availability process. But could anyone tell me what is actually wrong with this diagram?
One thing I'm sensing that our assumption was every collector don't have to have all the data, but I'm seeing like VA is having all of them.
Yeah. So VA has, we're saying like, oh, VA has its chunk for each POV. So say these are 5 different proofs of validity, and VA has, say, chunk A from each of those. It's not unheard of. Definitely that can be the case, but we don't assume that it would be.
So it will be 1 bit per one. I don't get this.
So what's going on here is that validators are stating which proofs of validity they have their chunks for, but then what's important here is so each validator statement is a row, but what's important here are the columns. So the bit vex that we described in our prior slide, these are rows in our later diagram here, and then the columns describe, okay, how many validators actually have their chunks for a single proof of validity. And then each of those proofs of validity would be associated with a single core. So core 0 would be the first chunks there in each of the rows, or the first column rather. We have another question in the back.
Maybe I didn't catch it. Why are the second and third squares X'd?
Yeah. So what's going on there is we have our 2F plus 1, that's 2/3 plus 1 of the active validator set must have seen this candidate, and they need to have said that they've seen the candidate, as in they have their chunks. So in this case, what we have is a set which contains 4 validators, and for columns, I guess if we're 0 indexing, then they're columns 1 and 2 here. For both of those columns, only 2 validators have seen their chunks of the proof of validity for each column. And that's only 2 out of 4. It's less than our threshold.
But why don't we use something like Merkle root and have just store the root by every validator, and if just one validator has at least one chunk, he can show it to everyone, and everyone can verify that it's the correct chunk, the integrity of the chunk.
What you're describing, so like a validator signing their statement that they have a chunk is, let's see. I guess what you're asking is, couldn't they prove that they have the chunk rather than simply signing a statement saying that they have the chunk?
I'm asking, why do we have to have consensus on a supermajority of validators having the same chunk? Why isn't it enough that at least one validator has that one chunk?
So what we're doing in this case is we're actually not trusting that each validator has their chunk. So the 2F plus 1 in this case, I went over it a bit earlier, but so that's from our 4th bullet point, that's our 2/3 plus 1. And that is actually derived from a couple things. Firstly, it's derived from our erasure coding. So our erasure coding, we have chosen to parameterize such that for Polkadot availability, we need 1/3 of chunks in order to reconstruct the original data. So 1/3 of the chunks that we need comes from just this erasure coding algorithm.
So here we're not providing the chunks, we're just saying, do we have them, yes or no?
Here, yes, we just say whether we have them, and later, once availability has been obtained, then particular approvers will request the actual chunks, and that's where approvers will actually use the well, they will actually use the Merkle proofs associated with each chunk to check that they are valid.
Okay. Okay. Thanks.
And one small extra thing, you mentioned that why do they have the same chunks? None of the chunks are the same. They are different chunks. They're for the same POV, and they will be used to reconstruct that POV, but they are different points on this huge line.
All right. So coming back to this diagram, the thing that I wanted to point out that is actually wrong with this diagram is validator Y is also in the active validator set. So not only would validator Y be constructing a block based on statements from other validators, but they would actually be involving their own statement as to which chunks they have. So we would not just have 4 rows here, we would actually have 5 rows, and validator Y would be represented in one of those rows. All right, we have another question.
So this doesn't have to do anything with the core times, right? With the cores, not with the cores.
So only so far as particular proofs of validity that are pending availability are assigned to certain cores. So like that scheduling aspect, there is some overlap there with execution cores there on that scheduling aspect. But as far as what's actually going on here and the, say, distribution of these chunks and the retrieval of these chunks and whatnot, all of that is very separate.
And each column of this is for single parachain. Because
yes,
we cannot have from different parachains in the same like relay block that we're creating, right?
What you have described is absolutely accurate for Polkadot today. Now, something that is enabled, or possible at least, with asynchronous backing is that we may, at some point in the near future, be able to make available and then approve 2 blocks for the same parachain within the same relay block. Now, the way that that's possible is basically dependencies, and then like the creation of those blocks would then be sequential on a parachain collator. So one collator would produce 2 blocks sequentially within the same 6-second window, so within the same relay block. And then on the relay chain side, the validators would process those blocks in parallel and would use one block as a prerequisite to the validation of the second block. So that's something that is on our wish list.
Nice, thanks.
All right, so now to talk about this, well, proof of validity chunk validation. What happens if there is a bad chunk in the reconstructed proof of validity? Well, before we get to the solution, well, with a corrupted proof of validity, when we're running the parachain validation function, that function might fail for a reason that's not attributable to our backers. So if somebody along the way has tweaked their chunk of the proof of validity within the data availability layer, then that's not the backer's fault. That's some random validator in the set's fault. And so if we were to just run proofs of validity naively and assume that they came to us in the state that the backers gave them to the validator set, then that could lead to the punishment of innocent parties. So we need some kind of solution to check the integrity of these chunks as they're coming in. And our solution is Merkle proofs. We just love them. So proof of validity chunks form branches of a Merkle tree in this case, and we distribute a proof alongside each chunk. Then later, when we are looking to check the validity of those chunks, we check it against this erasure root, which we have distributed in the candidate receipt for that candidate. So that candidate receipt is on-chain, and then the erasure root is also on-chain and available for any validator, say an approver, to later grab and to use for checking chunks.
So, sorry, when you say the candidate receipt, it's the block that's still going to be written?
So a candidate receipt is like a condensed representation of a parachain block candidate. It contains essentially a bunch of hashes. It would have like a state root hash. It would have an erasure root hash. Maybe, well, there are several other things that go inside that receipt, but essentially the receipt allows us to uniquely identify parachain block candidates that have been submitted to the relay chain, and then using that we can interact with these proofs of availability or proofs of validity that we have been sending around off chain. All right, so it's time to revisit erasure coding and actually go into some depth on it. So we encoded data of k chunks into a larger code word of in chunks. We are expecting that we can retrieve any k subset of those in chunks. We can recover any k subset of the in chunks using any other k, but the important subset that we can retrieve is the original chunks that represent our proof of validity. So the way that erasure coding is implemented within Polkadot is with a fast Fourier transform version of the Reed-Solomon algorithm, but there is a much better visually intuitive example called Lagrange interpolation, and we are going to look at that example just because it intuitively makes sense, potentially within the span of a single lecture, how this is all working and how you can use some data to retrieve other data. All right, so we had earlier some nice curves from Mache. Now we have more curves. So for any, I'll describe how how Lagrange interpolating polynomials work here. For any number of n of points xi, yi, there exists only one polynomial of degree n minus 1 such that p x of I, the polynomial function of x of I, equals yi for all I. So in this case, we have 3 points, like 1, 2 would be x1, y1, then 3, 2 might be x2, y2, and 4, negative 1 might be x3, y3. And those 3 points are only passed through by a single function that has, say, value, x to the power of 2 and fewer. So if x squared is the largest power of x, then this is the only function that would cross through those 3 points. That is extremely important for our retrieval of data later. Now to describe how is our set of chunks, these erasure coding chunks, how are these being turned into points that can then be fitted to a line? The index, if you remember, our chunk is both a vector of bytes, so it's a bunch of information, and there's also an index for each chunk. The index becomes our x value, and our bytes of bits are just interpreted as just a very large number. So our bytes are y values, and their indices are x values. And then we can construct some polynomial of a very high degree that is able to, I guess, perfectly pass through each of those points. Now, how would this look? So we have our initial on the far left here, 3 points. Those are indices for chunks, and then the large numbers described by chunks if we interpret their bits as raw large numbers. Then we are able to, with our 3 points, we can interpret this we can rather get our polynomial of degree 2, and once we have that polynomial of degree 2, what we can do is we can figure out more points that would lie on that polynomial. So for more values of x, we calculate the y. And from then on, we have 5 points, any 3 of which would retrieve the original polynomial, and then using that polynomial, we can get back our original 3 points, or original 3 chunks of information. We have questions in the back.
How is this different from Shamir's secret sharing?
I am unfamiliar with that one, so I'm afraid I do not know.
I think, okay, you want a mic?
Yeah, we could pass a mic over.
Yeah, hi, I'm Risho. So, in terms of interpolation, we are adding more chunks into the data, and after from those chunks we can construct our polynomial and interpolate the previous points as the data chunks, right?
Yeah.
What is the benefit of? My question is, we're adding more data, and and our main data, it's less, and we're adding more chunks to it, right? So what's like are we sacrificing also space and storage in terms of that, like adding more data, and also like how can we sure also those data won't be missing, like because we are protecting our on data missing, right? Because it should be available, so we're adding more data so that we can reconstruct it again. So what if all of those chunks also goes missing?
So, well, I'll describe the conditions in which all of those chunks would go missing. So 2/3 plus 1 of our validator set have said that they have their chunks. So in order for all of our chunks to go missing, we would need to have 2/3 plus 1 of our validator set being either dishonest or non-functional. So like their machines have broken down, or they are all malicious. And at that point, we've kind of broken our security model anyways. As far as how could this possibly be more data efficient if we are creating all this extra information? The answer is essentially that extra information, while it is larger than the original data, it's only 3 times larger in the case of Polkadot. So we store 3 copies of the proof of validity, but those 3 copies are spread out across the entire validator set of Polkadot. So that's 15 megabytes being spread out across the entire validator set, whereas maybe the best alternative that doesn't involve any algorithmic trickery would be having 1/3 of validators store a full copy of our original data. That would require us to store somewhere in the range of 300 times the size of the original proof of validity. So it saves us about 100-fold.
Also, in terms of comparing with other methods, this one is better for actually saving space and storage efficient.
Mm-hmm.
Okay, thank you.
And for the Shamir secret sharing question, this is Shamir secret sharing. Shamir secret sharing is using Lagrange interpolation theorem. It's just the math theorem behind Shamir.
All right. So, in summary, how does Reed-Solomon work if we're using Lagrange interpolation? So we divide the data into chunks of size p bits. Then we interpret those chunks as large numbers, mod p. And the index of each chunk is x sub I, and the chunk itself is y sub I. We then construct an interpolating polynomial, p of x, and evaluate it at an additional n minus k points. So the full encoding would look like what we have on our bottom line here. So y sub 0 through y sub k, those are our original information. So that's k different chunks of original information, and then p of k out to p of n minus 1, that is all the new information that we've created, say new points that we've placed on our graph that we then would be able to define a polynomial by. And in order to do reconstruction, all we need is some k-sized subset of all the points that we described here in line 5. But there's a final twist. So the final twist is Polkadot POVs are actually too large to encode in a single code word. What I've been describing this whole time is a single Reed-Solomon code word and how we would split that into chunks and distribute it. POVs are too large to encode in a single code word, and so there are actually many code words, each of which encodes a small subset of the original data. Nonetheless, the simple way that I described things, well, like all of our suppositions about how this system works remain the same, even though it's a little more complicated. And I'll describe with a nice visual how that works. I'll take a question first. Okay. Yeah, I believe I put it in the slides a little earlier, but maybe I didn't go into it in any depth. So a code word is the combination of that original data that you derived more chunks from and the derived chunks. So it's like one full unit of data and derived chunks. Yes. All right, and I'll take another question there.
Yes. So we are making sure the POVs are available, and there are multiple POVs per. Okay, one POV per parachain, right?
Yeah.
So, and you're saying like this, the full POV, it's large, and we cannot encode it like fully. We have to split it more.
Yes.
And then, so if there like a specific algorithm to split it before now going all the.
Yeah. So the splitting is pretty easy. I think it's literally just you can define breakpoints and just make them all even. So. And define those breakpoints such that each subset of your data can be encoded within a single code word, so there would be size limitations involved. But you actually just split it up. And it's fine maybe if the last piece of data is smaller than expected, you can still encode it with, say, a smaller code word, but there's just this maximum size to pay attention to. Now, how does this actually look? So we have our original payload. We've taken 2 out of the 6 chunks of it, and we haven't encoded them. Those 2 chunks end up, say, chunk 0 is paired with validator 0, and that's a chunk of original data. Then chunk 1 is paired with validator 1, and so on. And we have, in this case, 4 derived chunks that would be accurate to Polkadot's way of doing things, where we need only 1/3 of the chunks to recover the original data. So we triple the amount of data. That's 4 additional derived chunks. So this code word would describe 1/3 of our original payload, and in this example, then we have another code word, and that code word describes the middle portion of our data, and we have a third code word. And that code word encodes and describes the final portion of our data. Now, one data availability chunk is actually, so the chunk with, say, index I actually describes a bunch of smaller chunks that have the same index from within each code word. And because, say, validator 0 has chunk 0 from every code word, and because that's the same across all of the validators, we have this nice guarantee that if we can reassemble the data from any one code word, then we can actually reassemble all of them. And that's why we don't need to think about there being multiple code words, even though there are multiple. All right. So moving on, I'm going to speak briefly about some ongoing work that we're doing to improve this whole process. Reed-Solomon is costly. It takes 14 to 20% of validator's CPU time, based on our calculations. So this is an obvious target for optimization. we have a few ideas that we're working with to optimize this. One of these is called systemic chunks recovery, which, if done properly on a happy path, removes the need for Reed-Solomon decoding entirely. So let me describe how that would work. So you notice that validators with index 0 and 1 are the validators that have all of the original chunks of data. That is 1/3 of validators that have all of our original data. And other validators are entrusted with all of our derived data. Now that means that if validators 0 and 1 are honest and give us back the chunks that they decided to hold on to, then we can actually recover our data without decoding if we recover it from just those two validators. Like, we get our original data unmodified back. We don't need to undergo this very expensive decoding process. So instead, if we get back our original data, we do still need to do a little bit of work. We need to actually re-encode it using erasure coding, because we have this erasure Merkle root that we need to check the chunks against. And so we need those erasure encoded chunks in order to check them against the Merkle root. Now, if we, well, in theory, this would give us about a 50% CPU time improvement, because encoding takes about half as much time as decoding. Also, there are some nice tricks in terms of just code efficiency. We can get the compiler to elide some array bounds checks, and we can also do some inlining so that so that our compiler doesn't force us to look elsewhere for functions that are defined in one place. So altogether, these optimizations can give us another 33 to 50% CPU time improvement, depending on if we use unsafe Rust. And those improvements actually were implemented within the last month. So we are actively making this thing better. And finally, there's a really exciting potential improvement. There's a Reed-Solomon library that is better implemented in ways we know not, but it is 10 times faster than the one we are using. So if we can get a hold of that, apparently it's patented, but I don't know. If we can convince patent holders to let us use it or something like that, then again, that's a huge improvement in this, in this Reed-Solomon encoding process. All right, we have final time for questions, and we have another one in the back.
Yesterday we had a keynote with Gavin where he was talking about systems that don't care. But if these are systems that don't care, why do you guys care if it's patented or not?
Good question. We'll see if legal cares.
Yeah, I was just looking through the slides, the old ones, I guess.
Yeah.
We don't have the updated ones. And there's a slide where you have a comparison between approaches, and you mentioned, Dank Sharding and Celestia.
Yeah.
I was hoping maybe you could go a little bit deeper into that comparison between Celestia and Dank Sharding.
So I'm afraid those old slides were actually from a prior presenter, Andronic, and he is not here today. Yeah, those comparisons, let's see, part of it had to do with the actual proving that we have availability. I can at least speak to that. They were using a sort of random sampling of chunks in order to verify that they had enough chunks distributed without actually pulling in all of these statements from the entire validator set, and having this 2f plus 1 level that you had to meet. Essentially, they were finding it to be very, very improbable that data was not available via this random sampling. So that's one area where I guess a trade-off is made. But I can't speak, I'm afraid, to the rest of those protocols.
Sure thing. And one more question. So regarding the erasure encoding, and I'm just trying to understand a bit of the theory too. So it seems like, I believe you mentioned that the data is sharded, I guess, sequentially, right, across validators? Is that correct? Like, because there's an index you mentioned, right?
Yeah, and actually there's some more, there's some more work ongoing by which we might randomize the process by which chunks are assigned to validators, but for now it is sequential in that way.
So does that mean that, I guess, whoever's, doing the proof, or I guess checking to make sure that it's correct, has to know that index? Is that like part of a data structure or something? Because at the beginning I was thinking maybe there's like a DHT or something that maps to all the shards, but it seems like it's like sequential.
Yeah, so the validators know their indices within the validator set, and then each chunk actually has its index appended to it as well.
Got it. Okay, thank you.
All right, we have another.
Yeah, just simple. So one thing is every validator doing the erasure coding, or only one, and then we are trusting that person does it correctly, and then he splits up?
Yeah, so backers initially are doing the encoding, right? Because backers need to create these chunks in order to distribute them. And then the more expensive part is approvers are the ones doing the decoding a lot of the time, because approvers need to get the proof of validity so that they can approve or disapprove a block. So that's not very expensive to have the backers do this encoding, both because the encoding is more efficient and because there are fewer backers, probably a backing group of 3 who have signed off on this thing, whereas approvers, there are going to be probably 30 at least. So most of the work takes place on the decoding side.
Okay, thank you.
All right, with that, we can take another 10-minute break and come back for some Cumulus.